I still believe my wife was transitioning from primary school. Kind of falling on
Right? I mean, you know, Donna and Daniel were in and out of the show. We were at, I was with them. Pretty weird.
Yeah. A bunch of kind of like linear.
Okay, so welcome back everyone to the last talk of the day before the panel. So remember to stick around for the panel. So we're very happy to have Alex Lombardi telling us whether random quantum circuits are PRUs. There's some sort of like law, like is it Betteridge's law or something that like the answer to a question in a headline is always no, but I don't know what this applies here. I guess we'll find out.
All right, hey everyone. Thanks for having me here. Yes, I guess I am breaking the law a little bit in that I do actually want to argue the answer is yes, but of course the it's not so clear cut. The overall goal for today will be to give evidence for random quantum circuits computing pseudorandom unitaries. We will prove this under a hardness assumption that we think is likely to be true. But I guess that the jury is always still out on that, and we'll see what everybody thinks. So this is based on discussions with Fermi Ma and John Wright. Also, apologies in advance. This is not this project is not finished. There's no paper online. But if anybody has questions for me, feel free to talk to us afterwards if you want more details. Okay, so the topic for today is something that I'm going to call the random circuit heuristic, which is this informally defined principle that we believe that random quantum circuits of sufficiently large but polynomial depth seem to behave like random unitary operations. And there are a bunch of undefined terms in the sentence I just gave, but I think this is a heuristic / intuition that computer scientists, physicists, etc. Like to use in their work, and we're trying to investigate this a little bit more formally. So for today, we're going to pick a particular random circuit model to be working with, which is referred to as the brickwork model. I've drawn it here. So in the brickwork model, you have a sequence of 2-qubit gates that always connect adjacent qubits in the architecture. And in this model, every 2-qubit gate in the circuits is IID and Haar random among 2-qubit unitaries. So that's the random circuit model we're going to be working with. It's as far as I understand, a very standard model that people think about. And so why? Where did this heuristic come from? Why is it something that we care about? So to first order, I think the answer is that random unitaries are really nice. They have lots of cool properties that we'd like to take advantage of. But random unitaries also have the unfortunate property that they are not efficiently implementable. They require quantum circuits of exponential size. And so the hope of this heuristic is that we can write down a polynomial size circuit, use it in whatever application that we care about, and hope for the best and expect that maybe what happens would be similar to what would have happened if we used this inefficient random unitary. So in particular, maybe everybody in this audience knows this already, but let me list a couple of applications where I think this heuristic is being used. I would say it's part of the basis for these random circuit sampling based quantum advantage protocols. I'm not an expert in this stuff, but to the best of my understanding, the fact that you would expect these inefficient verification procedure to actually notice something interesting when you do random circuit sampling is based on the heuristic that it's like a random unitary. So that's one. maybe a clearer or an easier to understand application where it's clearer what's going on is that random quantum circuits are used to model quote unquote chaotic physical processes where I think the most well-known application or the most well-known example here is probably in modeling, say, the time evolution of a black hole, where when you observe what a black hole, observe the time evolution of a black hole, it seems to, one, scramble information. The unitary that's is happening appears to be unstructured unitary, but if you believe quantum extended Church-Turing, it has to be efficiently implementable, so it is not, for example, a random circuit. And so one reasonable thing that you can do is model it as a random polynomial size circuit, and then when analyzing its behavior, hope that what happens is similar to if you had a random unitary. Okay, so so these are definitely important things that are happening where understanding the behavior of random circuits is important. Finally, something maybe a bit less familiar to the audience that I still want to mention, and I think this is a topic that cryptographers are going to have to think about more over the next few years, is that this random circuit heuristic should be very useful in quantum cryptography. So here I would say it would be useful to take some inspiration from what cryptographers call the random oracle heuristic. In the random oracle heuristic, the basic principle is that if you design a crypto system that's defined relative to a random function, that's making queries to a random function, that if you instantiate it with a sufficiently unstructured and scrambly hash function like SHA-3, then you should expect the crypto system to be secure, to still be secure with this instantiation. And so what's happening here is somewhat similar, where you might have a cryptographic construction relative to a random unitary, and then you'd like to say that if we plug in a sufficiently scrambly polynomial size quantum circuit, that your application should still work, that you should still have whatever security you were hoping for. It's not directly analogous to the random oracle heuristic because the random oracle heuristic doesn't say to instantiate your function with a random classical circuit, but still I think it's reasonable to take inspiration here. And you could think about some maybe stronger version of the random oracle heuristic where you actually instantiate your, so it's easier to phrase in terms of when you're thinking about reversible computation. But if you have a random permutation that you'd like to instantiate, you could hope that plugging in a random reversible circuit of polynomial size classically will do the job of a random oracle instantiation. And so there the analogy is quite direct. Okay, so this is what I wanted to say on motivation. So the big question is, I'll move to the next board.
Alex?
Yes?
Just a quick question. Are you giving out the circuit description as well? Is that
So of course, there are many versions that, there are many situations you could think about. In the talk, we're going to be talking about PRUs where the gates are not going to be given out, but the answer is you could imagine either way. It's a valid question either way. Okay, so. Okay, so hopefully you're reasonably convinced that we have good reason to care about this question. In which case, now we can ask, well, is this heuristic true? And of course, that's always a tricky question to ask. But is it true in cases, and are particular consequences of the heuristic that we care about, are those consequences true? So in terms of what we know, we have, or the community has proved some pretty strong results on statistical properties of random circuits. In particular, we know that random circuits of a particular depth are what are called unitary T designs. This is the main results that I would say.
Just to make sure I understand the model, the Brickhoff model, the only randomness is in this.
The choice of gates, yes.
Yeah, this gate.
That's right. Yes, and so what I'm about to say today, you could apply to other circuit architectures, but we are basically never thinking about a situation where to other random circuit distributions, but we are always thinking about a situation where the architecture of the circuits, like the locations of the gates, is always public. Okay. Good. So good. So what we know is that for any parameter t of n, where n is the number of qubits being acted on by this circuit, that random circuits of depth d, which is some polynomial in n and t. There's also an error parameter that I want to ignore, but I will write it. So random circuits of sufficiently large polynomial depth are epsilon approximate T designs. I don't want to go into the details too much here, but basically what this is saying is that if you only make T queries, if you query your random circuit on T inputs, then what you see when you query a random circuit of this depth is epsilon indistinguishable from what you would see if you queried instead a random unitary. That's what we're going to say for today. Great. So this was originally established by a work, or as far as I understand, by a work of Brandau, Harrow, and Horodecki in 2012. But there has been a long line of work trying to understand to what extent random circuits are T-designed. I'm not going to be able to cite all of the works on this, but I do want to mention that a recent result of Chen, Ha, Haferkamp, Liu, Metger, and Tan, which sort of identified the exact function d here at which the statement seems to be true. It's or at least the key point is that it turns out to be true even for things that are linear in this parameter t. Okay, so this is a very powerful statistical property of random circuits. That is, we don't really talk about. It's not talking about the observations of just efficient algorithms. It's talking about the observations you can make by making T queries and then performing any statistical tests that you want. So this is what we know. I also want to mention, because it's relevant to something I say later, that this most recent work, proving the statistical property of random circuits, turns out to have this really cool implication for quantum circuit complexity, this thing called incompressibility. Where they show that that if you take a random circuit of depth d, then it is highly unlikely to be even approximately implementable. Sorry, not depth of with T gate with S gates. A random circuit with S gates is highly unlikely to be implementable by any quantum circuit with the number of gates equal to S divided by some sufficiently large polynomial in N. This is what they're able to show. So quantum circuit complexity, the circuit complexity of random circuits, of the unitaries computed by random circuits, goes up linearly as you increase the number of gates of the circuit. It's a really cool result that follows from the statistical property.
But do we know whether some compression is like how much compression could still be possible consistent with the best result?
Yeah. So well, maybe one of the experts should chime in, but I think the result is that if you have S gates, that this is separated from S divided by some moderately sized polynomial in N, and you could hope for better than this.
Yeah.
Okay. But before this, even something like this was not known.
Yeah.
So this is specifically for the unitary, right? Not for like measuring classical outputs. Right?
So I believe what they show something stronger, which is that if you think about the state you obtain by applying the circuit to all zeros, that this state cannot be generated by a circuit of this size. Okay. So this is what we know. But what I want to emphasize is that while this is a nice statistical property of random circuits, it's not really all that we're looking for with this random circuit heuristic. This is limited to statements about sort of tests that query the circuit on a number of inputs that is upper bounded by the depth or at least the number of gates of the circuit. Whereas it is very reasonable to ask, if you have some circuit of depth D, now I'd like to make a number of queries which is much larger than D, what is going on? And unfortunately, we know that you can't have this sort of T-design property in that regime, and so then it becomes you have to ask something else. So the appropriate generalization, the right thing to ask in that setting where you're making more queries than your depth or gate count, is this thing called pseudorandomness or pseudorandom unitaries. So that's the next question that we're going to ask. We're going to ask if random circuits are PRUs. As a quick recap, or a quick reminder, a family of efficiently computable unitaries U sub k indexed by a key is a PRU family if for all polynomial time oracle algorithms A, so it's an algorithm A, it makes queries to some unitary U. We have that, suppose for simplicity that A just outputs a single classical bit, and what we want is that an expectation over the key, what the adversary observes when querying the unitary UK is very close, is negligibly close to what the adversary would see if it were querying a Haar random unitary. In case people are wondering, there are a few different inequivalence quantum query models, and you should not worry about this. Everything that I say applies to all the different query models, and we should not worry about it.
Can I ask you a question? So is your goal to construct a PRU, or is your goal to put that this specific?
The latter. I want to understand if random circuits have this pseudorandomness property. Yeah, so yes, question?
I know this is a quantum workshop, but is there a classical analog of this, random classical circuits PRUs?
So you can ask this about reversible circuits. If you don't talk about reversible circuits, then they're biased and stuff is bad. But you can ask about reversible circuits. And in 1996, Gowers conjectured that they should be, and we don't know much beyond that.
Is there a classical analog to what you'll be talking about?
Yeah, it's the thing that I just said. Yes, and I'll mention it later. But the stuff that we're saying about random quantum circuits will also apply to this reversible classical circuit model. Okay, so everybody reasonably happy with PRUs? Yes.
When you said you you shouldn't worry about what the query model is, you mean things like whether you have access to the inverse or control and stuff?
Yeah.
Yeah. It's all the same.
Whatever. No, it's not. It's not all the same. But
The results will hold.
But yeah, for every one of those models, we'll have a result. It's a model agnostic. We're proving model agnostic statements. Okay. So great. So people were able to work hard and prove that random circuits are T designs. So why can't we prove that random circuits are PRUs? Well, it turns out that we know if PRUs exist, this has nothing to do with the random circuits anymore, but if any PRU family exists, then sharp P is not contained in BQP. So there are no BQP algorithms for sharp P, and therefore, if you are going to prove that these things exist, then you are resolving big complexity theory conjectures. And so, subject to us not resolving the big complexity theoretic conjectures, the best we can hope to do is prove a conditional result. So that's what we're going to talk about today, a conditional result. Okay. So, okay, that's fine. On the other hand, maybe you have the opposite worry. Maybe this is so strong that we should just not expect this to be true for random circuits. But so here we have some reason to hope, and this comes from this cool results from last year of Ma and Huang. What they show is that if post-quantum one-way functions exist, then PRUs exist. So again, this is not about random circuits. It says there exists a family of circuits that will compute a PRU for you. So it says that at least the cryptographic notion is not so strong that it's uninstantiable. Like under an assumption that we pretty strongly believe at this point, it is possible to build a PRU. Unfortunately, this doesn't really say much about whether or not random brickwork circuits or anything like that are pseudorandom unitaries. In fact, some of the inspiration for understanding how to construct PRUs came from these more physicsy or I don't know, let's say physicsy questions. But this existence result doesn't really say much about them. And I don't want to get into the details, but one reason why this doesn't seem to give us a very satisfactory answer here has to do with the model for computing pseudorandom unitaries and how it refers to ancillas. So this is what at least I think should be called an ancilla-free computation. There's a unitary that you're computing and you're not using any ancilla registers. And what they're and the PRUs that they analyzed here use a ton of ancillas that need to be initialized to 0. That will be 0 at the end, and you compute a PRU on the subregister. And anyway, don't worry too much about these details, but I really don't think that this has too much to say about this question. That's the main point I want to make.
I mean, they do give a construction, right? It's just not the random circuit construction.
That's true. Yes. Okay. So, all right. So with all that set up, let me state our results. Okay. So the main message that I want, it's a little complicated to state the results, but the main message that I want you to take away is that if random circuits are not PRUs, then there will be surprising algorithmic consequences. Yeah. So and in a word, what we prove is that if random quantum circuits are not PRUs, then there is efficient black box algorithm that learns and the depth of an unknown depth random quantum circuit. Learns the depth exactly with very high probability. So the assumption, so in other words, we're going to prove that random circuits are PRUs under a computational assumption, and the assumption is that it is hard to learn exactly the depth of a random circuit. And so, what should we think about this? Well, I guess maybe the first thing to keep in mind is that if you could learn the depth of a random circuit, then obviously random circuits are not PRUs. But hopefully or at least to me, it's not at all obvious that there should be a converse here. It's like a priori, maybe there's some reason why why random circuits are not fully pseudorandom that has nothing to do with this like exact depth learning problem. But what this says is that you have two options. Either they're fully pseudorandom, or you have an efficient algorithm for exactly learning the depth of a random circuit, which again, I'm not an expert in quantum learning theory, but I expect that this would be a very surprising result. Yeah.
Is it clear that this task is like information theoretically possible?
No, it wasn't until this. So we also prove that it's information theoretically possible, and we're not aware of any other way of proving it besides what we do here, which is crazy, and yeah, this should be fixed. But
Sorry, then what is information theoretically possible? Learning the depth?
Yeah.
Why can't you just do some classical shadows attack? Yeah.
Well, okay. Well, I'd be happy to talk about it, but we thought about it. We're not aware, and there's also nothing written down as far as we know. But please, yeah, talk to us if you think there's some easy reason. That would be good to know. Yes.
Is there some restriction on like how deep the random circuits are that you are considering, or is this just saying?
I'm being a bit loose with quantifiers here, but maybe it'll be good for me to write more. But the question is whether there is some polynomial depth at which points random circuits of that polynomial depth are PRUs, and that turns out to be equivalent to the question of whether there is some polynomial depth at which it becomes hard to learn the depth. Yeah.
So back to Lowen's question, do you have a PRP analog of this?
Yes. Yes.
So, but basically this means that it's going to be very hard to prove this assumption, because proving this assumption implies this.
I mean, yes, it's also hard to prove that one-way functions exist, right? But
you don't need to prove that one-way functions exist in order to.
Yes. So yeah, one motivation you might have in the world is can we hope to just unconditionally prove quantum cryptography exists, like escaping complexity theory? That's an important and interesting line of work. What we're saying doesn't have much to do with it. We can't prove that PRUs exist without, there is this complexity theoretic barrier.
Exactly.
But so what we're trying to do now is reduce, we hope that random quantum circuits are PRUs.
Yeah.
We would like to reduce this to as weak of an assumption as possible.
This is kind of the weakest possible.
Well, I'll try and mention open problems. I think you could maybe hope to weaken the assumption, but.
Okay, but in the sense that if you can learn the depth, then it's not a PRU. So, you need to assume you can learn the depth.
Yes, the assumption is necessary, but you could still. Maybe an even weaker looking assumption is also equivalent, right?
Okay.
Yeah. Okay, but I'm sure everybody has understood this already, but let me just spell it out. So what we're considering is learning algorithms. We have an algorithm A. It has query access to a circuit C. So the situation is, just to make this problem well defined, what I'm going to do is I'm going to give you some upper bound on the depth. I'm going to say you're querying a circuit of some depth that we'll call D star. You don't know what it is, but I'll give you an upper bound. The depth is some D star less than or equal to a D that you know. And now you can make queries to the circuits, and your goal is to try and output this depth d star exactly. This circuit has some. I generated it to have some particular depth. Your goal is to figure out what it is. And the goal is to do this, say, to be correct with probability at least like 1 minus the little o of 1, to be correct with like quite high probability. This is what I'm going to ask of the algorithm. As long as this task is hard, as long as this cannot be done in polynomial time, then random circuits will be PRUs.
In the worst case, for every there's no.
No. This is still a random circuit.
Oh,
No. It's still an assumption about random circuits.
Okay, got it. Like this brick.
Yes.
Got it.
Yes.
For what distribution of these stars?
It's not distributional. It's worst case. So yeah, in other words, the assumption will be like for every polynomial time a, there exists a d star such that a isn't working. A isn't computing d star on random circuits of that depth.
And so with probability is just over A, it's not over the.
And also the choice of C.
Okay. But for there exists some d star such that for C drawn from that.
Yes, that's right. Yes. Yeah. So our theorem is assuming depth learning is hard for some upper bound d, which is polynomial in n, then random circuits of depth some capital D, which is also polynomial in n but a bit larger than this d, are PRUs. Okay, so that's the main theorem statement. So let me mention a few comments on this. As far as I know, this is the first construction of a PRU under under an assumption which is not known to imply the existence of one-way functions, and moreover, an assumption that seems like it could be true even given the power to invert one-way functions. Of course, you could always tautologically assume that some construction is a PRU, but I would consider this to be a non-tautological assumption. Yes?
No, it doesn't imply one.
Sorry, what?
After your result, it does imply one-way functions.
Why?
The assumption.
Why is that?
Because I thought under this, you said that there is random circuits are PRUs, right?
But that doesn't give a one-way function.
Okay. Oh.
Yes?
I guess maybe he's saying that if everything has a classical analog, then it's
Yeah. No,
actually, no.
So I didn't understand.
If there is a classical reversible analog of this, then it might be hard to justify that this is actually no quantum. If this is secure, then there's also no.
But what do you mean? The classical analog will be that it's hard to learn the depth given classical queries. They're very the assumptions are quite different, right?
I think that there is no PRG without one-way function.
Yeah.
The classical thing breaks.
Yeah, exactly. Yeah.
It's actually, if you can hope to prove, if there is some way that prove that this assumption quantum condition, then maybe you can also hope that that will also generalize to constant, and you also prove one-way functions.
I see. I'm not sure. I'm not sure if I agree, but I'm also not expecting that we're going to prove this assumption tomorrow or anything. So, yes.
Do you have any upper bounds on learning the depth?
So, yeah, you're saying, do we have any algorithms? What algorithms do we have for this problem?
Where is it? Can we do it?
Yeah, I mean, it's, before this work, I think it was just known that if you make a exponential in the depth number of queries, that you can learn. But one consequence of this result, I guess maybe Will's saying that maybe it should be possible to prove.
Sure, that was known because this doing this information theoretically implies an incompressibility.
Yeah. Yes, I'm getting there. But I agree. I'll say it in a second. But yeah, before this, we just knew that if you make an exponential number of queries, you can statistically. Right. It depends on what you're trying to learn. Yeah. In fact, we had no results actually on learning this depth exactly. There are some like related learning results. So like there are results saying that you can learn, for example, a circuit that like you can learn a low depth circuit that is close to the circuit that you started with. For example, you can learn the description, but that's different from outputting the depth because maybe this circuit C has an equivalent circuit or approximately equivalent circuit of smaller depth. That's like this is this incompressibility thing that Fermi was talking about. Yes.
So then, does your result mean that there does not exist?
Yes, we're getting there.
Okay.
So you're using n, the number of input wires, as the only scaling parameter. Could you?
No. I have this depth as a function of n.
Exactly. I mean, but n is the number of input wires, right?
Yes.
So could you hope to introduce an additional security parameter and get scalable PRUs from this?
I thought about this.
Be a poly of lambda independent or with a weak dependence on n, and could this assumption still hold?
Yeah, hold on. I thought about this for a second, but let me think about it offline so I don't say something wrong. But I agree it's an important question. Yes.
Does this result generalize to say that, like, if it's hard to learn the depth of some distribution over circuits, then PRUs exist?
So the result does not just hold for this particular distribution over circuits, but, and well, okay, I guess TBD ongoing was the exact best statement we can make. We can say it for certain other kinds of distributions of bounded depth circuits, but like there are quite a few constraints. Like it's like circuits where you have repeated IID layers or something like that. Like that's the kind of thing that we can talk about maybe. But yeah, there are some pretty strong constraints on what kinds of distributions we can argue about, which come out of the proof, which I'll try to sketch at least. Okay, so in terms of notes on this theorem, yeah, it's an interesting PRU construction that doesn't seem to rely on one-way functions. It gives you a PRU like on the in an ancilla-free computational model. And we have classical analog of this theorem for random reversible circuits, like classical circuits. And finally, I'm skipping over some pretty important details here, but roughly speaking, because you prove this by a reduction, you say if you can break pseudorandomness, then you can learn the depth. We know that in a polynomial number of queries and unbounded computation time, you can break pseudorandomness of like any polynomial size circuit family. I think so. Anyway, certainly for these. And so if you run this reduction and carefully check that you actually can, then what you get is a polynomial query, statistical learning algorithm, like depth learning algorithm. So you also get poly query, statistical depth learning algorithm. And I would be very interested to know if there is any way of proving this other than the proof that we give. We weren't able to find it, and indeed, it proves this like very strong, technically incomparable, but very strong incompressibility results for brickwork circuits. It says that if you like okay, this is like not exactly the truth, but for intuition, like if you think about like the distribution of unitaries that you get by writing down a random depth D circuits, and the same thing for depth D plus 1 circuits, like if you can statistically learn the depth from queries, then what it's saying is that these distributions are like nearly disjoint, really far apart.
Sorry, when you say statistically learn, you mean you ask polynomial queries and then you have infinite times?
That's right. That's right. Yes. And so yeah. And so what this is saying is that like if you sample a random circuit of depth D and you think about the unitary that it's computing, the exact depth is almost perfectly defined. Like except with a tiny error, you know exactly what the depth of this circuit is. So it's saying that like an added. Now there are some details here, but it morally says that like an additive compression by one depth is impossible.
So is it useful on self-free PRU?
I'm sorry, say that again?
Is it useful on self-free PRU?
I guess I don't know what you mean by is it useful. Like cryptographically useful in cryptographic instructions, I'm not sure. I haven't thought about it. My primary motivation is just the scientific question on its own, like what's going on with random circuits. But I do expect that ancilla-free PRU should be useful for something, but I haven't thought about it. Yes?
Was this depth learning thing known for classical reversible circuits before?
Oh wait, okay. I'm not sure. It may be easy in this case, but I don't know. But like they're like it's morally it should be easier because then you're just talking about truth tables, right? Like yeah. There it's just you have a truth table and it's somehow easier to understand the question.
But this is something like a minimum depth.
Yes. That's right. Yeah. So again, it's not exact. There's some like tiny interpretational issue with this, but yes. Yes.
Does this also extend to seeing there are states which can be prepared with D plus 1?
No.
Oh.
No.
It is fundamentally about queries.
Yes, I believe so. I don't think there's an easy way to talk about this for the state circuit complexity.
If you like construct the choice state or something, that doesn't work. It's kind of like seeing the average output.
No, that might work.
It might. It's yeah. We have started thinking a little bit about this, but it's yeah. Okay, so with the remaining time, let me try and give you some details about how the proof works. But yeah, my main takeaway is this seems unlikely to me. It seems unlikely that there's an efficient algorithm for this. And so I am now more confident that random circuits should be PRUs, and hopefully you are too. But I'd be interested also to, yeah. Maybe somebody thinks that this actually should be easy. That'd be very interesting to think and or talk about. So hopefully, yeah, I'd love to chat. Okay, but about the proof of this theorem, let's see. Okay, so our goal, so like our setup is we have some polynomial time adversary A, and it has the property that it distinguishes depth capital D from Haar random unitaries for some like large polynomial capital D. And what we want to get out of this is a distinguisher, or not a distinguisher, something that learns the depth, learns depth D star less than or equal to some upper bound little d for random circuits drawn from that depth. So how might we do that? our reduction is a sequence of a bunch of like pretty small and hopefully like understandable steps. So so here's one simple observation. So we're trying to learn the depth exactly. If you could learn the depth exactly, like where the depth is like unknown in worst case, then clearly you could distinguish if I tell you you're either querying depth D0 or D1, then clearly you can tell which, right? If you really could learn the depth, then you can tell whether it's depth D0 or D1. Convenient thing for us is that in this high probability regime, if you're learning it, if you're correct with extremely high probability, then this is actually an if and only if. So if you can distinguish between any pair of depths, then with a union-bound loss, which is not too large, then you can learn the depth exactly. So it suffices to be able to distinguish depth D0 from D1 for any pair of depth D0 and D1 up until that bound. Yeah, and the reason is that you can, provided that you can solve this distinguishing task, you can learn the depth by running all like D squared distinguishers and then looking for the like unanimous winner. You can think of each distinguisher as like voting for which depth it is, and there's going to be one unanimous winner with high probability, and you pick that one. Okay, sorry, this is slightly sketchy, but hopefully you can simulate that. Okay, so now we know it suffices to be able to distinguish between any two depths. And I also want you to believe me that like it doesn't matter what the difference between these two depths really is. Like I'm going to give you an argument as to why you could distinguish depth D from depth D plus 1, and you should believe me that it applies just as well to distinguishing any pair of depths. I'm just going to
distinguish with very high probability.
Yes, that's very important. Yeah, because otherwise these things are not equivalent. Yes. Yes. Okay. So next so now our goal is to distinguish depth D from depth D plus 1. And actually our goal is a bit more complicated, but this is just to simplify notation. It doesn't affect anything. Okay, so this is what we want to do. Now, how are we going to do this? It's a few steps. In step 1 of the argument, so we start with this big guy that distinguishes depth capital D from har random. Suppose that this initial algorithm makes T queries. Like it's a particular algorithm that we're starting with. It makes some polynomial number of queries, call that T. Then by our T design property, we actually know that har random unitaries to this specific algorithm are indistinguishable from random circuits of depth, which is some polynomial in T. So given this, we know that our original adversary distinguishes depth D from some depth D prime, which is polynomial N and T, it's important to keep track of how well we're distinguishing. So like Yael said, we want to distinguish with high probability, with very high probability. What we know here is that we have some small epsilon advantage. Here, our initial algorithm has some small advantage over random guessing, and now we still have some small advantage over random guessing. Small but inverse polynomial. Okay, step 2, we apply a standard hybrid argument. If you can distinguish depth D from depth D prime, then there's got to be two adjacent depths that you distinguish. So in particular, the same A will distinguish depth D plus I from depth D plus I plus 1. for, say, a random, if you want for a random I, with advantage, which is still like basically epsilon. It's like epsilon over d prime. You lose a polynomial factor in your advantage, but it's you've still got an inverse polynomial advantage distinguishing two adjacent depths.
Do you mind starting a new board because there's a podium that blocks?
Oh, you can't see? Okay. Okay. What should I erase? I guess I'll erase this. The leftmost? Okay. All right. Okay. All right. Now, okay, these steps have been pretty generic. Everything that I'm going to do from now on basically boils down to the following like principle. Like random circuits have like nice self-reductions that you can do to them, and we're going to use this to great advantage. So first, like a minor modification here. I said I'm distinguishing depth d plus I from d plus I plus 1. Notice that this I really doesn't matter. I could have just said that I'm distinguishing depth capital D from capital D plus 1. And the reason for that is like a padding argument. If I have query access to a random circuit of one of these two depths, then I can append myself a random circuit of depth I, and then emulates whatever this algorithm was doing. Okay. So great. So now I can distinguish depth capital D from capital D plus 1 with a very small advantage, but non-negligible. And in the end, what I want to do is distinguish depth little d from little d plus 1 with very large advantage. So yeah, that's what's left to do. We want to amplify the success probability. And the way that we do it is inspired by some results on hardness amplification in complexity theory. So for example, there's this there are famous results like this thing called the XOR lemma, for example, which says that if you have a function that is mildly hard to compute, then computing the XOR of a bunch of independent copies of that function is very hard. And so yeah, there are a bunch of results in complexity theory that kind of look like this. They're not directly applicable to our problem. They for one thing, we're in a different computational model than the model that people normally study these questions in. But it turns out that you can use I guess our proof is heavily inspired by how some of these proofs work. And so if like the rest of the proof, if you've seen, for example, before the proof that the proof of this XOR lemma using Impagliazzo's hardcore lemma, if you haven't, don't worry about it, it's fine. But if you know this stuff, then what I'm about to say should sound familiar to you. Okay. But so let me, and I don't have enough time to explain the full details of this argument, but let me sketch at least a little bit about it. So it turns out that if you want to strongly distinguish like two depths, depth little d from little d plus 1 on a uniformly random circuit, the way that we'll do it is by solving this distinguishing or prediction problem with small advantage, not on uniformly random circuits, but on all high entropy distributions of circuits. And it shouldn't be obvious how these two things relate to each other, but it turns out that they're related. So in step 3, what we do is we show that there is an algorithm that is for all distributions D supported on depth D and D plus 1 circuits. There exists an algorithm that predicts the depth with advantage something like the same thing as before, like epsilon over, some like constant times, like constant, like related by a multiplicative constant to the previous advantage. So achieving small advantage. But the key point here is that we're predicting the depth not on the uniform distribution, but on whatever this high entropy distribution is. So yeah, so for all distributions supported on these circuits with high enough entropy, you get this.
Small d or capital D?
Little d. This is the step at which we shift from big D to little d. So here we had uniform distribution on capital D depth. Here we're having non-uniform but high entropy distribution on little d depth. And so this is what we're showing. And I'll say a word on how this works. Also notice that the algorithm here is allowed to depend on the distribution. So it looks kind of weird, but this is correct. This is really what I mean. And like in one sentence, the way you do this is you embed a circuit C drawn from D inside a product of IID uniform circuits.
So A sub D uses D as a black box?
So what's going on actually is that this A sub D is a non-uniform algorithm which has advice that are a bunch of samples from D.
Exactly.
But at a very high level, the way you can hope to solve this distinguishing task is by embedding your one small circuit inside a big uniform circuit, thinking of the big uniform circuit as a product of a bunch of small uniform circuits. And since this distribution has like high entropy, what it means is that you can sort of see this distribution inside one of the copies of the circuits that you sampled. I don't have more time to explain. You can ask me after if you want, but this is at a high level how it works. And then finally, like the last step that you, in order to get our actual like good learning algorithm, is an invocation of von Neumann's min-max theorem. So like what step 3 is saying is for all distributions D satisfying some constraints that I placed on the distribution, there exists an adversary which is efficient according to some constraints. Like there are constraints on the adversary's running time, number of queries like this. There exists an adversary depending on this distribution that weakly predicts depth on C sampled from this distribution given query access. For all there exists. So in other words, min over distributions, max over adversaries, distinguishing advantage is large. Min over D, max over A. Distinguishing advantage is at least some like epsilon. Then the min-max theorem says that you can switch the max and min if you consider mixed strategies over adversaries. So there exists a distribution over adversaries such that for all distributions on these depth D and D+1 circuits, this single adversary distribution achieves large distinguishing advantage.
But is it clear that this adversary is efficient? Because it's distribution.
So the support space for the strategies in this game is efficient adversaries.
Yeah.
So it's a distribution over efficient adversaries. It's not efficient. The distribution may not be efficiently sampleable. Yes. But what it says is that there's some distribution over pieces of advice such that if you sample your advice, like adversary's advice from that distribution, you can weakly predict depth on every high entropy distribution of circuits. And then finally, like, it's finally at this point that it turns out that you can amplify. Now you do a naive repetition, basically. So the actual depth learning algorithm is you obtain samples A1 up to some AL of adversaries from this good distribution, and then you majority vote what they say, right? So you have a circuit. You have query access to a circuit. You run each of the adversaries with query access to this circuit separately. Each of them has a prediction. You majority vote the predictions. There's some analysis which I'm skipping, but you can argue that this works.
Interesting. So basically, your A's not just are non-black box. You really don't know how to construct.
Yeah, this reduction is non-explicit. Yeah.
Interesting.
There are some like uniform min-max theorems, and so maybe I haven't thought about it, but yeah, at the moment it's non-explicit. And yeah, so that's what I want to say about the proof. And then maybe just like let me, if I can have 1 minute to state a couple of open questions. So, So one reasonable thing, one very natural thing that you could ask is, well, can we weaken this assumption? Can we say that random circuits are PRUs, assuming that some even harder task is hard? And so although what I'm about to say is maybe incomparable, but like morally weaker, one could hope to say that random circuits are PRUs, provided that learning the circuit is hard. That would be great, right? So is it true? Yeah. Can we prove that random circuits are PRUs if learning an entire circuit description is hard? Great. Perfect.
Quick
New
question.
paper.
For this, it's fine to learn any circuit that computes the same thing, right? It doesn't have to be the specific circuit.
That's the way that I'm formulating it. So yeah, there's some, and there's a reason for this. Like at least in some models, it's not possible to like recover the C that was sampled. That may not be possible. But you can ask, can you recover a circuit that's approximately the same, that computes approximately the same unitary as the original one? It feels like the stuff we're doing here could be related to that. And yeah, if you want to discuss or have thoughts, I'm happy to. But yeah, we don't currently see how to do it. Then question 2 is there, and the answer to this definitely should be yes, but like, is there a more direct statistical learning algorithm for depth? Because the thing that we know how to show is that there exists, like non-explicitly, there exists a non-uniform algorithm, like a family of quantum circuits that will learn this depth. There's no way that should be the truth. There should be a simple, direct algorithm for doing it, but yeah, it implies some really strong incompressibility. So it would be very interesting to be able to show this. Yes?
Actually, why doesn't your reduction give you success probability exponentially close to 1?
Because I didn't explain this. But yeah, I can explain afterwards. But you don't get that from here. There could be a set. There could be an inverse poly-dense set of circuits on which this algorithm just fails.
And do you know what the inverse poly is?
You can tune it. Yeah.
Tune it.
It depends on the entropy here. Like it's a tunable parameter.
Okay, so what's the optimal?
No. It's like whatever inverse poly with respect to the depth you want, you'll get an algorithm but for a little d that goes down as the poly goes up.
Some fixed poly.
Any fixed poly is fine. So maybe we should talk about it afterwards. Right. Then the last question I want to ask, because this incompressibility statement, or sorry, this statistical learning algorithm feels very much like an incompressibility statement, but it's technically incomparable for reasons that I can explain if you want to know. But like getting this getting a traditional incompressibility results from this. Using these techniques would be very interesting because you'd get a sharper one. The reason that this doesn't follow immediately is that this is saying these distributions don't overlap, but it somehow doesn't technically rule out that maybe like there's some somewhat dense sets of circuits that have some smaller circuits. Anyway, it's because the incompressibility asks about the existence of a circuit and not about these distributions, they're technically incomparable. So it'd be nice to understand the connection to the traditional incompressibility statement better. That's what I'll say. So yeah, thanks a lot for listening, and yeah, cool.
Thanks for the talk. Let's do maybe one question, and then we'll have the panel right afterwards, so you can ask more questions then. But
so does the same analysis work if instead of a PRU, we are thinking about a PRS, and instead of learning the depth given queries, you're learning the depth given like some fixed output state of the circuit?
Hold on, let me think about this for a second. Fermi, do you have any idea?
I think probably not. Because this like requires like self-reducibility properties of unitaries that they don't think will work for states.
No, but it's still a random circuit. You're okay. Instead of
no, but it's like okay for PRS, like you're given your unitary applied to a random basis state from a subspace, right? That's the problem. You want to distinguish that from Haar random. Like here, like when we're doing these like reducibility arguments, we're like if like you started with an algorithm which runs a circuit on a particular input, you're now like when you run this reduction, you're now going to be running like whatever inputs you were running your circuit on before. Now you're going to be running it on like that input state multiplied by a new random circuit. It's not good at preserving like these like input distributions. So
you can pad more layers onto a PRS sort of after the circuit was applied. You can't pad more layers before. Like you can't take C0 and then put more layers between C and 0.
Yeah.
And we need that.
And we need to be able to do this.
okay, maybe we should stop here and take a very quick 5-minute break and come back here at 4:45 for the panel. So all the speakers from today's session, please stick around and we'll try to set you up. Gives quantum advantage.
It'll give you some circuit, but not the